Okay, thank you.
Everything working? Hello?
Yes, you are audible.
Okay, so thank you very much and good afternoon everyone and greetings from Finland. So my name is Aleksi Peltonen and I'm here today to talk to you about the benefits of formal verification in protocol standardization. So my goal for the next half an hour is to convince you of the importance of security verification, particularly in the early stages of the design process of protocols. More specifically, I will be focusing on explaining the symbolic modeling of cryptographic protocols and discussing how it can be used to prevent security vulnerabilities in protocol standards. I'm going to start this talk by discussing protocol standardization and explaining a bit about how the verification part fits into this process. After that, I will show you a couple of examples of recent verification projects that I have been involved in. So, one of my main research goals for the past few years has been contributing to different protocol standardization organizations by formally modeling and verifying protocol standards. I have been working on protocols developed by organizations such as the IETF, 3GPP, and GSMA. I have in particular focused on analyzing protocols in the early design phase in which they can still be changed before standardization. And a bit later in this presentation, I will talk a bit more about why
Sir, excuse me.
Okay.
Sir, your slide is not moved.
I'm just introducing the topic. Can you see the next slide?
Yeah, okay. Now it's
okay.
not.
Yes. I will change slides as the presentation goes on. Okay. So first, let's discuss a bit about why protocol verification is important and why it is worth spending time on. And we'll start by talking about the attack surface. So distributed computing is everywhere these days. Over the past 2 years, the increasing performance requirements of information systems and services have created a trend of scaling these traditional systems by distributing computation power over multiple subsystems. This is then further amplified by the emergence of new technologies such as the Internet of Things that require high-speed connectivity over both traditional and mobile networks. So because of this, new security protocols are constantly being introduced by both standardization organizations and also companies in order to fulfill the requirements of these new use cases. So from a design perspective, a core challenge of designing these cryptographic protocols is the requirement for them to function securely in open environments such as the internet. And in order to make this possible, a fundamental assumption of protocol design is that any and all communication takes place over an unreliable channel, which is either entirely or at least partially controlled by a malicious entity. And this is particularly important to consider when designing protocols that involve exchanging confidential data over some network. So this includes any information that you might, for example, send over the internet, but would not want anyone else to read or modify. And because of this, the procedures such as authentication and key derivation must resist both passive and active inbound attackers that try to learn confidential information or otherwise interfere with the communication. Now, many of the widely deployed network protocols and cellular protocols that we use daily, such as TLS and 5G, are developed by these standardization organizations, such as IETF and 3GPP. And both of these organizations have taken the initiative to combat security risks in distributed systems by developing and standardizing protocols that follow strict quality requirements. These requirements typically involve reasoning about security and ensure that, at the very least, known design flaws have been considered and avoided to the extent possible. So by the time developers implement these standards, they often have extensive security guidelines available. For example, the IETF currently requires all of its standards to have a section describing security properties and considerations. Similarly, in recent 3GPP standards, intra-network trust is assumed to be decreasing over time, and security is considered a core aspect of the updated protocol designs. However, once the initial development phase is completed, protocols are typically then released as standards, which are then deployed and released to consumers. Now, this is of course just a simplified generalization of reality, since in many cases, larger standards, such as many mobile network protocols, may already be deployed to at least some extent during the standardization process. And as I mentioned, even though most modern protocol standards are extensively analyzed and tested before deployment, new vulnerabilities are constantly discovered and used to perform some large-scale attacks. So for widely deployed protocols, more often than not, someone eventually discovers some kind of flaw in the design, allowing malicious entities to exploit vulnerabilities, which then needs to be corrected by the developers of these protocols. And now this can sometimes be a very lengthy and time-consuming process, which is especially dangerous if we already have some consumers using the protocol outside of sandbox test environments. And in such cases, we do not only need to create the fix, but also deploy it and roll out the updates. And this is where formal verification steps in. So by introducing formal methods into the standardization phase, many of these attacks can be discovered and prevented. And these verification methods can be used to support the standardization process of security protocols by detecting vulnerabilities as early as possible, ideally already before any implementations have been made. So now that we have gone through the benefits, let's talk a bit about what formal verification actually is. To put it simply, it is a group of methods based on computational logic that can be roughly divided into deductive and model-based verification. So deductive verification resembles logical proofs and involves using axioms and interference rules to determine the correctness of a protocol. But as mentioned in the beginning, we are in this talk going to focus on the modeling approach. So in model-based verification, we create abstract models of protocols by representing them as states and transitions. So here a state refers to the global state of the distributed system during the execution of the protocol. It would include information such as process variables and attacker knowledge. Model checking can then further be divided into computational and symbolic modeling. So in the interest of time, I'm going to skip the computational approach and instead focus on symbolic modeling, which works on a slightly higher level of abstraction. So in this approach, we represent protocol messages as terms of first-order logic with data fields as variables and cryptographic primitives as function symbols. Protocol goals or security properties are then expressed with a property specification language such as temporal logic, which is all less complicated than it might sound. So basically the idea here is to create an abstract model of the protocol and try to figure out what could go wrong or what an adversary can learn from eavesdropping on honest participants. And one important thing to note is that we do assume perfect cryptography. This means that without proper keys, it is impossible to, for example, fake signatures or break encryption. We also assume that the used encryption methods are flawless and correctly implemented. So basically, we ignore any brute force guessing and software bugs since we are focused on analyzing protocols on this abstract level. Our adversary typically follows the standard Dolab-Yao model, which makes them an active attacker that controls the entire network between honest parties. So in other words, we expect the attacker to intercept all messages and to be able to delete, modify, replay, and spoof messages, of course provided that they have access to the relevant cryptographic keys. In summary, we assume that the honest parties follow the protocol meticulously, and the attacker is sort of the worst case scenario for an adversary. And now if we can show that the protocol can withstand this, then we know that the design of it is reasonably robust, at least from a security perspective. So now that you have an idea of what we're trying to accomplish, let's move to the practicality of the verification process. So the process typically involves modeling the protocol in some input language and specifying the desired security properties, which we then try to prove or disprove through methods like state space exploration or constraint solving. And the properties that we're interested in are typically related to things like confidentiality, integrity, or availability. And now to make life a bit easier for ourselves, we don't have to do all of this manually, and instead we can use protocol verification tools to automate parts of the process. For example, let's imagine this simple protocol consisting of only one message. The message is sent in plain text from Alice to Bob and contains a secret code which we'll call X. Now, by modeling this protocol, we can use a verification tool of our choice to analyze different aspects of the protocol. For example, let's say that we want to know whether an attacker is capable of modifying the message, thus violating its integrity. In this case, the answer is of course yes, since we don't have any encryption. So here you can see our tool managed to prove that integrity is not achieved by providing us with a contradicting counterexample that shows how the attacker can intercept and modify this message. And this is of course an extremely simple example. However, as I stated in the beginning, we are these days developing more and more protocols every day that are getting increasingly complex. And in many cases, these tools make it possible to identify extremely complicated and specific attacks. And in the interest of time, we're not going to go into the details of any specific tools. However, I will be mentioning them later in the case studies, and for anyone interested, I highly recommend looking them up. So all of the tools that I have used and will be mentioning provide excellent documentation with many examples of syntax and features. And many of these tools also have very active and welcoming communities around them. So with that being said, let's dive into our case studies. Next, I will present you two different protocols for which formal modeling led to the discovery of some security vulnerabilities. In the first example, I was actually one of the authors developing the protocol, but for the second one, I had no direct connection to the standardization process. So the first example comes to us from the Internet Engineering Task Force, and it's a protocol called Nimble Out-of-Band Authentication for EAP, or EAP-NOOP for short. EAP here refers to the Extensible Authentication Protocol, which is basically a framework that allows developers to define methods for device authentication. EAP-NOOP specifically is used for secure bootstrapping of IoT devices. Basically, it connects your device to a wireless network and a remote server, and it is intended as a generic bootstrapping solution for any kind of device that has no pre-configured credentials, such as certificates or passwords. The method specifically targets devices that lack the traditional input and output capabilities, which we commonly use for authentication. So this could be anything from, let's say, speakers and monitors to maybe fridges and cameras. Basically, anything you want to connect to the internet that lacks a keyboard and a display. So here on the slide, you can see an overview of the EAP-NOOP architecture. An execution of the protocol consists of two or more in-band steps and a user-assisted out-of-band step between them. So during the in-band exchanges, the server and the device trade configuration values and perform an elliptic per Diffie-Hellman key exchange. All the derived keys and configuration values are then authenticated in the out-of-band step, which could, for example, be the user scanning a dynamic QR code with their phone or even just recording a blinking LED light. This protocol was standardized as RFC 9140 by the IETF in December 2021. And as I mentioned in the beginning, an essential requirement for any protocol to become an IETF standard is that its authors manage to convince others of its usefulness, correctness, and most importantly, security. So like any other RFC, EatNoob also underwent multiple iterations of updates and improvements before eventually becoming standardized. From the security perspective, formal revision played a crucial role in designing this protocol. Early on in the design phase, we developed two different formal models of the protocol, which we then kept updating until the final version. And this allowed us to not only detect potential issues in the early design drafts, but also to make sure that updates of the design did not break anything or introduce new problems. So the first of our models we created with the Micro Common Representation Language 2, or MCRL2, and analyzed it with the associated toolset. So MCRL2 is a language intended for analyzing the state space of process interactions in distributed systems. The goal of this specific model was to identify any possible deadlock situations caused by prompt messages. And in fact, this model resulted in the discovery of two potential denial of service vulnerabilities in the design of the protocol. Both of these cases required extremely specific attack scenarios that would have been difficult to detect without the model, but once we had detected them, fixing them was not too complicated. And besides the vulnerabilities, modeling the protocol forced us to be precise about its design and security goals, which then helped us avoid some ambiguities in the specification. The reason for this is that writing the model requires you to be specific about a lot of the details that go into the protocol. By then comparing the model with the specification, it becomes a lot easier to spot potentially unclear sections. The second model of EatNoob was created with another tool, which is called ProVerif, and this model was specifically for identifying potential misbinding attacks. So in an identity misbinding attack, we have an adversary that takes advantage of the lack of verifiable identifiers to pair the wrong two endpoints together. If no pre-provisioned credentials exist, such as password or certificates, physical access is often used to identify the correct devices. And this is also the case for EatNoob. So through the modeling process, we confirmed that the attack exists and came to the conclusion that it unfortunately is an unavoidable consequence of the lack of these verifiable identifiers. So this one cannot be completely avoided. However, the same is true for many other protocols such as Bluetooth, for example. In this project, the tool we used did not only help us identify the attack in not just EatNoob, but several other protocols, but it also provided us with 5 different variations of the same attack. And if you're interested in the details of the attack or the modeling phase, we have published 2 open access articles which explain the attack and show some of our analysis. So our next case study is a protocol specified by the GSM Association called Remote SIM Provisioning, or RSP. In the first example we just discussed, we modeled an early draft of the protocol which had not yet been implemented or standardized. In this project, the goal was to analyze a widely deployed protocol and tried to find potential vulnerabilities so that we could provide recommendations for future versions. As the name of the protocol suggests, it was designed for downloading these SIM profiles into mobile phones. Specifically, it makes use of the embedded SIM or eSIM, which is a modern alternative to physical SIM cards. So the eSIM is a chip on your phone, which can be programmed with identifiers and credentials that the device uses in the authentication and key agreement to gain access to your operator's network. And there are two variations of this protocol. We have the machine-to-machine version, which is used in remotely controllable devices, such as IoT, and we have the consumer version, which is used in consumer devices, such as smartphones, tablets, and wearables. And this is the version that I assume some of you might have used before. So in this example, we'll be focusing on the consumer version. It was standardized by the GSM Association in 2016, and the first commercially implemented consumer versions were created around the same time for smartwatches. Since then, in addition to wearable devices, many flagship phones have also been released with eSIM support, and many of the major carriers globally offer eSIM contracts. The main benefit of using an eSIM contract for your average consumer is that you do not have to physically visit a store to get a new SIM profile, and you're not limited to only one profile at a time. So if you're, for example, traveling abroad, you can download a prepaid SIM profile from a local operator to avoid expensive roaming charges. Then once you leave, you can just delete the profile. From the operator's perspective, it also significantly reduces logistical and production costs, since there is no need to keep producing and shipping the physical SIM cards. Now, this all sounds great, but as I mentioned in the beginning of the talk, anything that we decide to connect to an open network has the potential to be compromised by an attacker. The security of the protocol used to download these profiles is especially critical because in this protocol we transfer the credentials with which your phone or device will authenticate to the mobile network. So if a malicious party would gain access to your profile, it could lead to identity theft, billing fraud, eavesdropping, and various other privacy violations. So in this project, we decided to analyze the security of the consumer RSP protocol with the covert verification tool that I briefly mentioned at the end of the previous example. So we modeled two different variations of the protocol and analyzed security properties related to mutual authentication, profile binding, authenticated key exchange, and profile install notification. Here, our analysis showed that the protocol does in fact protect against a network adversary, but only if all the intended participants are honest. So this means that there should be no malicious operators, servers, or compromised devices anywhere in the world. Since this is not very realistic, we decided to also model the protocol in several partial compromise scenarios by giving our attacker access to different entities that are supposed to be honest. The security failures in these partial compromise scenarios actually then revealed some weaknesses in the protocol design. Maybe most importantly, we realized that the security of RSP depends sometimes unnecessarily on being encapsulated in a TLS tunnel. Of course, TLS is one of the more thoroughly analyzed protocols, but in this case, it does not necessarily have to be used from a security perspective. And furthermore, as with EVE-NOOB, the lack of pre-established identifiers means that a compromised server or device can be used for attacks against RSP between the honest participants. And finally, the lack of reliable methods for verifying user intent can also lead to some serious security failures. So based on our findings from this modeling process, we recommended several practical improvements to RSP implementations to future versions of the specification and also to mobile operator processes to increase the robustness of eSIM security. And once again, if you're interested in the details, we have published an article summarizing the work and also made all of the formal models available on GitHub. So we have now discussed two different cases of research projects in which formal verification was used to identify potential vulnerabilities and attacks. So in the first one, the protocol, its implementation, and formal models were all developed by the same group of people. Using formal verification, we were able to identify some ambiguities and design issues that have previously gone unnoticed, not only by us, but also by others reviewing the drafts. In the second example, we analyzed an already widely deployed protocol. So in this case, we showed that it in fact fulfills the security requirements, but only when no honest participants are being compromised. So here, our model allowed us to analyze hundreds of variations of the protocol with different partial compromise scenarios. And as a result, we suggested some improvements to future versions of the standard that would provide the protocol overall with stronger security guarantees. So with that said, we are now nearing the end of my talk. And in summary, I have given you an introduction to formal verification of security protocols and presented these two different case studies to show the effectiveness of these models. Thank you very much for your attention. As I mentioned previously, all the material I have discussed today has been published in open access research articles in case anyone is interested in the details. And if you have any questions, I would be more than happy to answer them now. Thank you.
Thank you, Mr. Aleksi. Any